Hi, hello everyone. I'm Joyce, presently the British Society for Geomorphology Postgraduate Forum Chair. So, welcome to our April's webinar. We organize a webinar series every month based on different methods and different things that we explore in geomorphology. This is mainly a postgrad initiative, but we extend and try to bring in different people across the geomorphology. Uh, so we have Dr. Gabriel Kaless today. So Professor Kaless is based at the Department of Civil and Hydraulic Engineering at National University of Patagonia in Chubut province in Argentina. Uh, he completed his PhD from University of Padua in Italy, and presently he is working on fluvial and hydrological processes of ephemeral streams in Drylands, as he's going to speak today on that. And since 2017, he has been working to monitor small basins, which are basically less than 100 square kilometers, with rain gauges and cameras, especially to measure rainfall and flash floods in this region of Argentina. Currently, he's working in the field of hydro-sedimentological disconnectivity and trying to assess all these rivers, especially in the lower section of the Chubut River. And besides this, he's also interested in the socio-hydrological aspects. He has been conducting series of interviews to understand how people perceive these landscapes and how people perceive these ephemeral streams. And he's trying to create an oral archive of last large flood which happened in 1958. He has a range of publications, which one of which he is going to share us today, and the recent developments, what he has done. So thank you, Gabriel, for agreeing for this webinar, and hopefully we will be enlightened with your findings from Argentine Patagonia. Over to you, Gabriel. Thank you.
Okay, thank you, Shayesh, for this introduction. First of all, for the invitation. I am really very happy to be here now today and to share with you our findings about this research. So thank you, Shayesh. Thank you to the British Society and for you to be here listening to this presentation. So this is the title of a publication we did a couple of years ago. When I received the invitation, I was thinking that it could be a good opportunity to enlarge, to explain with details the methods we are using and to introduce, include other findings that we have uh, done. We have continued working since the publication, so I have included new material that is not included in this work. Okay, I would like to make a short introduction about the knowledge that we have about ephemeral streams in dry lands. I will read most of the presentation, so I will not go by the branches away. So I will read, and I hope that my strong Spanish English will not make an interference. So there are some works, and one of the most famous monitoring experiences of the Walnut watershed in Arizona, which has been operated since the mid 20th century. And we have another interesting experience in the Negev Desert, which was more focused on sediment transport and shields. And there is another work in Australia, the Nason and Knighton in the Channel County. In South America, in contrast, fluvial systems in drylands information are still scarce, apart from a few studies on flash floods in the Atacama Desert. There remains a significant knowledge gap, especially in Patagonia. So, many of the studies in Patagonia are linked to the effects of flash floods in communities. Most scientific and technical studies have been carried out after major events, flash floods, documenting extreme flash floods in places such as the southern Sinai, eastern South Africa, and the southwestern United States. You may remember the Costa and Jarrett work about flash floods. In Argentina, similarly extreme events have happened in recent years across semi-arid Patagonia. Here you have the cities that were flooded in recent years. Puerto Madryn, I am living near Puerto Madryn, Comodoro Rivadavia, and the tablelands, the mesetas in the inner of the Chubut province. During these events, however, quantifying flood intensity is extremely difficult due to their hazardous nature, short duration, and the occurrence in remote areas. We have to travel 200 kilometers to catch these floods. So this is the lower Chubut River Valley where I am be talking about. I live here near Rawson, and the university is in Trelew City. And all these cities, Labon, Gaiman, Trelew, Rawson, belongs to the lower valley of the Chubut River. It is irrigated, and the head of their irrigation system is in Boca Toma. You can see farther on the left the Dique Florentino Ameghino Dam, and between the Boca Toma and the dam, there is a large basin of 1,000 square kilometers. Short duration, high intensity storms in this basin generate pulses of very high turbidity, which repeatedly interrupt the drinking water supply. In addition, these events have caused flooding in the valley, both in the past and in recent years. So the study was motivated by two main issues, water quality and flood risk. We will focus on the Sagmata stream basin, located halfway between the dam and the irrigated valley, which previous studies conducted in our department had identified as one of the most important contributors of runoff and sediment as well. So this is the Sagmata pilot basin. The basin has its headwaters at the Montemayor Plateau at 274 meters above sea level, and its lower point is at 53 meters above sea level at the outflow of the basin in the Chubut River. The climate in the study area is semi-arid. Average annual rainfall does not exceed 170 millimeters, and annual evaporation sums more than 700 millimeters. The prevailing winds are from the west as a result of the general atmospheric circulation. Here you have a map of geomorphological units. In terms of geomorphology, the study area is mostly composed of erosional forms excavated on hard volcanic rocks and soft sedimentary rocks, such as exhumated planation surface, structurated terraces, wetlands, and erosional scarps. Here we have a picture. These geomorphic features are not evenly distributed across the basin. For example, wetlands nearly cover 1/3 of the Charito and Rayum subbasins, whereas the Tirjalen subbasin has mainly fluvial landforms. Here you can see the headwaters of the Charito subbasin. At the top of the image is the tableland formed by the Rodados Patagonicos, and further downslope you can see the erosional scarps. The picture in the bottom shows the landscape as seen from the tableland. You see the recent deposits at the footstep of the erosional scarps. Remember this picture because I will talk about the flood out. This is the end of the channel, and I will talk about this flood out soon. So I will talk about now about the methods. One of the problems here in Patagonia that there are few records of rainfall, and distances are very, very long. From here to the Andes, we have 600 kilometers. So there is not research that can give us information about the spatial distribution of the rainfall. So one of the first aims that we had was to get information about the spatial and temporal structure of the storms. We installed 4 rain gauges to cover the Charito and Tirjalen subbasins, although site selection was somewhat constrained by limited access across ranch lands. We also developed custom data loggers, allowing the instruments to operate in the field for several months, even years, without maintenance. This is a map of the current situation. We have now 7 rain gauges, and these are the Thiesen's polygons that we use to make the calculation of rain averaged in the basin. At first, we recorded the rainfall using a 30 minutes time interval, storing accumulated rainfall during this period. But after the first event, we noticed that it was very large, so we reduced the time interval to 5 minutes. The equipment resolution is 0.5 millimeters. So this is more or less known methodology. And with regards to the size of the rainfall, we use these 2 indexes to find out the size. One of on the left you have the simultaneity index, and on the right you have the uniformity index. The simultaneity index is a modified version of the correlation index using the 0 instead of the mean value as a reference value. And the uniformity index compares the total rainfall depth recorded at pairs of rain gauges. Both of them compare to rain gauges. So if similarity and uniformity index were both high, we interpreted that the storm was as large as the distance between the instruments. Okay. I have a video. This is a capture of the video. I hope that we will have enough time in the end of this presentation to show you how it is seen the arrival of the flood. I will make now comments about how we did to register or to construct, to build the hydrograph. This part of the presentation is much more complicated, mainly because direct measurements are impossible. Not even if, and even if they were possible, they will be dangerous, building critical fumes that, like the ones that have been built in the Walnut Station, was not an option because of the high cost. For these reasons, we rely on indirect methods to reconstruct the hydrograph, and that is what I am going to explain now. So, building the hydrograph requires a fairly complex methodology. The variable that we actually measured was the water surface elevation, and discharge is then calculated using topographic data, hydraulic modeling, and continuous monitoring and bed elevation. As a result, we not only obtain the hydrograph, but also derive additional information such as the bore speed, transmission losses, and runoff volume for each subbasin. For each subbasin outlet, we selected a representative channel section. The section had to meet several requirements for hydraulic modeling. You see the section here with the orange dots. These requirements are: the channel had to be straight, avoiding curves or complex morphology. Roughness needed to be uniform along both the bank and the bed, meaning consistent vegetation cover or geological settings. And finally, the cross-section had to remain uniform. Basically, it had to be an engineering channel to reduce complexity in the hydraulic model. Bien, because of the remoteness of the sites and the lack of roads, we designed a system that was simple to build, had a low maintenance and low cost. Each gauge station consists of a PVC tube, 175 millimeters in diameter and 1.6 meters high. This is because we put there bottles to take samples of the water and sediment mixture. A graduated scale was painted on the tube at 5 centimeters intervals, and a time-lapse camera was installed on the near bank, taking one photo every 5 minutes and producing a daily video. To allow night measurements, a lamp was mounted at the top of these tubes. Here you see the Sagmata gauge station, and this is the Tirhalen Ridge or section. Because the channel is composed of a sand-gravel mixture, we needed to evaluate vertical bed changes during the flood and their effect on discharge estimates. So we installed 3 score chains across the channel located upstream the gauge station. The well were excavated to depth between 50 and 70 centimeters, depending on the presence of the clay layer. After each event, the exposed length of the chains was measured. In addition, we conducted annual GPS service surveys to measure random bed elevation along each ridge, allowing us to assess ridge averaged elevation changes. And a drone flight was carried out and ground control points were surveyed in the field to evaluate the vertical uncertainties. Okay, this is my favorite part of the research, hydraulic modeling, but I promise you that this is the only slide with partial differential equations. We applied a depth average model based on the RANS equation, the Reynolds average Navier-Stokes equations. Here we see the momentum and the velocity components. The momentum, these 3 equations have to be solved with the turbulence closure. I made some exploratory trials and found out that using complex turbulence model was not necessary. So I finally used the parabolic viscosity model. This model is based or calculates turbulence based on local hydraulic variables, so there is not a transport model to be solved. For the interaction between the bed and the flow, I used the classical Manning's formula, and all these components form the basis for the EVER software. On the right, you can see some typical outputs, the depth of the water, flow velocity, this is the magnitude of the vector, the eddy viscosity, and the bed shear stress. The last 2 pictures were more important for me to understand sediment transport processes. So, reconstructing the discharge from water surface elevations recorded by the cameras was far from straightforward. We initially assumed steady flow conditions, although we know that steadiness is not usual at all in these streams, essentially during the rising limb of the hydrograph. You may remember Richard Chan's publication of 1949. He talks about the wall of water. We didn't see here a wall of water, but we have measured very high rates of rising of the water level. I remember 15 centimeters per minute. The procedure was as follows. First, we determined how long the model needs to reach the steady state. This is step 1 you see on the top, on the right. Then we reduced the grid size step by step and estimated errors in predicting water surface elevation. We used the grid convergence index, and this allowed us to select an optimal grid. Next, we built a rating curve assuming steady state flow. Finally, we compare predicted and observed water surface elevations. Starting from the observed stage, we estimated the discharge, ran the model with this hydrograph, and extracted the predicted stage at the gauge station, and finally compare it with observations. You can see the step 5 and 4 in the bottom of this picture. So if discrepancies were between these results were found, I adjusted the flow so as to match predictions and observation in cases of an unsteady flow. And finally, the question is, which is the error or the uncertainty in this procedure? The main sources of uncertainty are, first, the channel roughness. We found a sand layer that we think it is related with the fallen limb of the hydrograph. Beneath this sand, there were gravels, so Manning's coefficient may change during the hydrograph, during the flood. But most important is the bed elevation. We used information from the chains to figure out the range of fields and score. And finally, there were some difficulties in reading the gauge scale from the images. We employed this formula. This is a classical theory of propagation of errors. And in the middle, you can see a graph that shows the ridge average bed change through time. There is a first period of degradation after the March event of 2019, and then there is a progressive aggradation process in the following less intensive floods. Well, overall, the error is more or less 13% for Tirhalen, Charito, and Rashun. It's acceptable. And at Sagmata station, we had 19% of uncertainty. Okay, this is new. It was not included in the paper I mentioned at the beginning. As we will see soon, we assumed that certain hydrograph characteristics are linked to the topology of the stream network. In particular, we wanted to identify areas where the flow spreads, such as downstream of floodouts. To do this, high-resolution Google Earth imagery was used to map the location of floodouts and other structures, such as bifurcation. And we used Sentinel images near infrared bands to calculate this index, the moisture index, and the I. I have another picture here. See this one. Two images before the event were taken so as to calculate a basement, a condition, a baseline dry condition. And then we compare, in this example, the March 11 with the March 18 images to have the difference of these indexes. And finally, we have the index on the right. And this image can be used to identify the regions that were flooded and remain wetted after the event. Okay, let's see some results from this research. I made a selection of the main topics of this paper. During the 4-year monitoring period, we had 13 meteorological situations that generated 17 flood events. These events produce 243 millimeters of rainfall, but the runoff was 24 millimeters, so the 10% of the falling water. Rainfall, simultaneity, and spatial uniformity were both high, suggesting that the storm systems are typically larger than 9 kilometers. This is the longest distance, the highest distance between rainfall gauge and rain gauges. So this is consistent with the dominant rainfall mechanism in eastern Patagonia, where precipitation is mostly associated with stationary frontal systems and convective storms are less frequent and spatially limited. This is the case of event 1 and 2 that I have highlighted in this image. But most of the events have, I see 80% have similarity index and uniformity index above the first quantile of the population. With regards to runoff, the runoff coefficients were calculated for each event and subbasin and show a clear decrease with basin size. Mean values range from 32% in the smallest subbasin, the Rashun subbasin, to 9% at the outlet of the whole basin. Runoff increases with the maximum intensity of the rainfall in 30 minutes, with the strongest relationship observed in the Charito subbasin, as you see here. We also tested whether the storm structure influences runoff generation, but differences were not statistically significant. We wanted to see if the first peak in the rainfall makes some difference if it was placed in the beginning of the rainfall or at the end or another place of the rainfall. We also derive channel processes information such as the bore's velocity, comparing the cameras between Charito and Sagmata, and Rayun and Charito, and the time lag. The bore velocity was calculated between 1 and 2 meters per second. When the channel was initially dry, maximum velocity was around 1.5 meters per second, increasing to 2.0 meters per second when the previous flooding occurred. So here we see the effects of transmission losses in the bed channel. In this slide, we see the relationship between the time lag and the peak discharge. The time lag between the rainfall intensity peaks and the discharge peaks increases with the stream length as expected. It is a proportional relationship, while intense floods tend to arrive earlier. I mean, I have to say 2 words here because there are theoretical research that suggests that concentrations times, this is another hydrological variable, depends on the rainfall intensity. It's not fixed to the physiographic properties of the basin only. And these results are important for understanding hydrograph transformations within the drainage network. This is the main topic of the paper and the research here. So these are the 4 types of hydrograph styles that we have seen in this basin. 3 of them have already been observed in Australia by Knighton and Nason. I mentioned their work previously. We added another one, the flat top hydrograph. I found a publication from the Walnut Station that they mentioned that they make a comparison between 2 basins, and they mentioned this flat top style. We identified 4 styles in this basin. The single peak hydrograph features a fast rising limb, and after the maximum stage is reached, there is a fast to moderate falling limb. Here you see figure A, this case. And I would like to say something about the flat top. The flat top hydrograph has the rising limb that can be fast or slow, but once the maximum stage is reached, it is maintained for a relatively long period of time, I mean several hours. I will go to the next slide so we can talk about these shapes. So to understand this diversity of hydrograph and most of all the relationship between the rain and the hydrograph, we used this simple conceptual hydrological model. It is composed of four boxes, sorry, control volumes. And the first one refers to the cloud, and the link between the cloud and the next one, that is the soil, is the rainfall. The rainfall connects the first control volume with the next one, the soil surface layer. Here, infiltration takes place. Infiltration is mainly controlled by soil texture, rock outcrops, or surface pavement and vegetation. Then we have the third control volume, the hill slope. Here we can here water can be temporarily stored in depressions or move downslope as overland flow through small rills or very small channels. At this stage, hill slope processes dominates, I mean storage and flow resistance. And finally, these small rills and channels feed the drainage network where channel processes take over. I mean storage, flood routine, and transmission losses. So we will talk about these four boxes and try to understand the transformations for each case. First, we start with the smallest subbasin, the Rashun subbasin, which has an area of nearly 6 square kilometers. At this scale, the general behavior is to reproduce the rainfall style. You see that it happens in 33% of the events. We analyzed the temporal structure of rainfall, which is related to the number and sequence of high intensity periods. And we found that events in which rainfall and hydrograph show the same number of peaks are typically characterized by hydrograph with a high intensity rainfall pools greater than 4 millimeters per hour. Occurring at the beginning of the event, followed by lower intensity sub-events. We interpret this behavior as being mainly controlled by processes associated with the first two control boxes, control volumes, the storm, and the soil. So infiltration, remember that this sub-basin has the major proportion of badlands, almost 1/3 of the basin is covered by badlands. Here you see the transformation. For instance, on the left you have the rain style is a single peak, and in the Rashun subbasin we have 3 cases of with this style and one of a flat top hydrograph. This is the dark blue case. Let's move to the next scale, the Charito subbasin. In this case, sorry. The Charito subbasin has an area which is 5 times larger than the previous case. So we start to expect that additional control factors take place here. Okay, in fact, the rainfall style is directly translated into the hydrograph in only about 1/3 of the cases. And we actually observe a reduction in the number of peaks. We also notice that the peaks are less clearly separated. This suggests that storage processes are operating both on hilltop and within the channel. And furthermore, we did detect the effect of the channel topology in one particular event. You remember event 1 and 2 that I mentioned that were convective events. In this case, rainfall consisted of a single peak, very intensive and with a short duration pulse. And despite this simple rainfall structure, the response of the basin was with a two-peak hydrograph. So overall, the influence of drainage network topology becomes evident only during rare, short-lived events that partially cover the basin. Let's talk about the Tirhalen sub-basin. This basin behaves quite differently. We observe the flat top hydrograph, basically independent of the rainfall style. It happened in 10 out of 14 cases, events. This very uniform response points to strong controls such as infiltration, hill slope storage, and channel topology. The basin has more permeable soils and the highest cover of dense vegetation. Both of them enhance infiltration and reduce runoff. Hill slope are more gentle in this subbasin, which increases surface storage and flow resistance. And finally, one of the most interesting features of this subbasin is that it has a low drainage density and a highly disconnected network with flatouts and bifurcation. These features spread the flows over the flat plane and creates a clear reservoir effects. And finally, let's see the time. I will say a few comments about the Sagmata Basin. We have here a scale of 100 square kilometers, and at the outlet of the basin, we see clear transformations in the hydrograph style. There are no compound hydrograph, only two cases where the number of only two cases where the number of peaks is reduced, and in one case, similarly to Charito, a single peak rainfall produced a multi-peak response at the outlet. Overall, this suggests that channel processes dominate at this scale. Okay, I would like to dedicate some minutes to the topic of hydraulic disconnectivity. This is a map for the March event, the 14th and the 15th March 2019. The colleagues from Aberystwyth will remember this event. Now let's talk about the disconnectivity. In this case, there were two storms, one on the 14th and the other one the following day. Here you are looking to the headwaters of the Charito subbasin. The flatout have been mapped and are shown on the right, no, here in the left, with yellow dots. When the stream leaves the erosional scarp zone, it enters into the Piedmont, and this is where things change. The blue patch shows where the flow spreads over the surface. This is actually the only case of flow spreading that we observe in this subbasin, because further downstream, the flow becomes well confined again and remains strongly channelized. Here we have a picture of the flood in the headwater I mentioned earlier, and the photo was taken looking upstream. What you can see here is a very wide and very shallow channel. In fact, it's hard to even define a clear cross section. Here the flow spreads out across the entire Piedmont, and this is another picture 1 kilometer downstream, and we found the channel pretty confined. So let's see what happens in Tirhalen subbasin. We see long sections of the main channel where the flow has spread out and occupied the adjacent floodplain. If you look closely, there is a very good match between a very good agreement between the wetted areas shown in blue on the left and the geomorphic unit named as the recent deposit, which is the area shown in light green or light yellow color. I'm highlighting just one ridge of this stream, but this pattern and this picture is repeated further downstream along all these geomorphic unit. This analysis was actually done after the paper was published, and it strongly supports our original hypothesis that slow flow over the floodplain creates a reservoir effects, which helps explain why we see this flat top hydrograph style in this subbasin. And I have a picture. You can see the end of the channel. It is hard to identify the channel in this picture, but you can see here the debris indicating the level of the water after the flood. Okay, so where do we go from here now? Right now, we are working on improving the technology we use to measure water surface elevation to make those measurements more precise. I didn't mention this earlier, but the uncertainty analysis shows that this variable alone, the water surface elevation, accounts for up to 90% of the discharge uncertainty at high levels. So improving this variable is a clear priority. We are also exploring ways to safely measure flow velocity, at least at the water surface. For this, we are using large-scale particle image velocimetry. We were actually lucky enough to record one flash flood in the field, and we are now making some trials with the software, the river, that was developed by the University of Cordoba here in Argentina. And finally, I am currently working on developing an index, a connectivity index based on processes, hydrological processes, with the aim to link the sediment sources within the basin with the samples that we have collected in the gauge stations. And here we have some words of Richard Chance, referring to the wall of water. Not many people see them, but those who do never forget them. I was thinking about the day that we were in the field and got trapped by the stream. So here we have the conclusions. This is actually a summary of the findings. We have seen four styles, and runoff generating storms are generally large in spatial extent and mainly associated with frontal system, but we have registered a couple of convective events. Across the basin, we identified these four hydrograph styles, which depends on the scale of the subbasin, the frequency of observation. So at small scales, basin response is largely controlled by rainfall structure and surface processes like infiltration and storage. At intermediate scale, the topology of the drainage network becomes increasingly important. The Tirhalen subbasin stands out of with its flat top hydrographs, which we link to high infiltration, gentle slopes, and a very disconnected network. And finally, at the basin outlet, all these signals are integrated, flashy upstream responses shape the peaks. This is the signal that come from the Charito subbasin, while slower contributions help attenuate and infill the hydrograph. This is the role of the Tirhalen subbasin. So I think that we have some minutes to see this video that we prepare with the first three events. And you can see now some aerial views of the gauging stations. So this is the map with the first four rain gauges at the beginning of the research. This is the Sagmata, sorry, this is the Charito station along the Sagmata stream. This one is the Tirhalen stream. More or less the dimension is 6 meters, the width of the channel bottom. This is the, the place where the gauge station is placed. And finally, this is the Sagmata station that summarizes or registers the contribution of the whole basin. This was the first event that I mentioned that we had set the rainfalls with a time step of 30 minutes. And after this event, we decided to change it to 5 minutes. You see Rashun first, then Charito, which is downstream, and finally Sagmata receives the wave. This is the following day. Pretty dry the channel. It was like a flash flood. And this is the second event. 2 weeks later, we had started the research in December 2017, and for almost 1 year we had 0 events. You see first the arrival of the flood in Rashun, Charito, and later in Sagmata. And I wanted to show you the March event with the flat top hydrograph in Tirhalen. Let's go back. So we have here 2 events, one in the day 14 and then 15. This is the first day. We were visiting this place with Hewell and Stephen. Or in the morning, 5, 7. Oops, we had a problem, Charito station. And look at the Tirhalen. The high stage remains for several hours, and the other 2 stations are already dry. This is 2 in the afternoon. Okay. Okay. Okay, this was the last slide. Thank you very much for your kind attention. And if you have any question, I will be glad to answer.
Yeah, thanks, Gabriel. It was wonderful. Like, yeah, it's one of the best presentations that we have seen. Thank you so much for sharing all your reviews on it. So, yeah, I think Professor Ian Reed has some questions. So, uh, Ian, you can unmute yourself and ask.
Yes. Well, Gabriel, congratulations, in fact, on being able to find out, in fact, exactly what is actually causing the differences in the hydrograph response. I did, though, in fact, actually wonder, you will know in that in the Negev, we have actually got a very interesting pattern of storms that, in fact, actually differentiate themselves between frontal rainfalls, which tend to be very low intensity and long lasting, and convective storms, which are in fact intense, but in fact spatially highly discrete. These storms, in fact, actually do in fact move around in a very predictable fashion. And relative to the orientation of the catchment, we find that they themselves, in fact, also actually create a difference in the hydrograph. So, for example, in fact, when moving upstream, up the catchment, they will in fact actually produce many more peaks in the actual hydrograph than in fact if they actually, for example, remain relatively stationary, or as with the frontal rains, they are in fact actually ubiquitous in the actual catchment itself. So I wondered whether or not, in fact, you find this, in fact, yourself, in fact, whether, in fact, there are occasions when, in fact, there is a relationship between the movement of a convective storm and the actual configuration of the drainage network. Could I make just two other observations, in fact, which are not really particularly controversial? But I'm quite interested that, in fact, your runoff coefficients, in fact, can be quite high. So, in fact, in some cases, in fact, you actually, I think, have runoff coefficients of something like 30% or so. Although, in fact, you do have very much lower runoff coefficients for some of your subcatchments. And in the Negev, what we've found is, in fact, that the runoff coefficients are, in fact, much less than 2% for all rainstorms. And the other observation, which I've got, in fact, comes from work that I'd done some long time ago in Kenya on planar sandbed streams, is, in fact, that the roughness coefficient, which in fact we were able to find was suitable, in fact, for these planar sandbed streams of 0.023, is coincident with the ones that you've been using, in fact, for your hydraulic modeling. So those are the points, in fact, I'd like to make. Thank you.
Sorry, would you mind to repeat the third topic about the coefficient roughness? I couldn't understand the question.
You chose a roughness coefficient, if I remember correctly, in fact, of 0.023, 0.024 for your channels, and that is in fact actually a similar value to the ones which we were able to find for planar sandbed channels in northern Kenya a long time ago, when I was working out there in the 1970s and 1980s.
Okay. Runoff coefficients, yes. In fact, I should say 30%, and the Rashun subbasin, the smallest one, and this is the better. I will refer to this subbasin because there is one rain gauge in the middle of the subbasin, so the measurement of the incoming water is pretty well calculated. And for the first event, it was 30%. And the second one, I mean, I am referring to this event of March 2019, it was as high as 60%. So all the clay and in the badlands were wetted, and it was surprising to find such a high value of runoff coefficient. But in the rest of the basins, such as Drylands, we are talking about sandy soils, so runoff is quite lower, 10%. And regarding to the movement of the convective cells, I mentioned one case. It was really very concentrated rainfall. Drylands didn't produce any major flood. It's an elongated basin, so it is very sensitive to the place where the water falls in this basin. In the other one, Charito, because the rainfall was in the headwaters and the timing of the channels were different, we have two peaks instead out of one peak rainfall. So we had few cases where we could see these effects. And but according to what I have seen in literature here, we have more. I had discussion with the reviewers about the measurement they do in Arizona and other places where they have very concentrated rainfalls. No, it is not the case here. And finally, with regards to uncertainties and the roughness coefficients, I found, making all these formulas, that it was not so critical, the roughness coefficient. Instead, water surface. My concern, my preoccupation was about where is the bed placed during the flood, because all the simulations, when you make hydraulic modeling, assumes that fixed bed. It's like a concrete channel. So I think that the geometry of the cross-section area is more relevant. Fortunately for us, we had not erosion on the banks, so the uncertainty was only in 1 degree of freedom in the bed. No, so
okay.
thank you.
Okay, good.
Thanks, Ian. Yeah, Stephen, you can go ahead.
Yeah, thanks, Gabriel. Really enjoyed that presentation. Obviously, you referred to the March 2019 events that we got caught in when we went out to visit those sub-basins. So it's good to see the results from those gauging events. I think that quote is very apt that you included at the end. That those who have, very few people see them, but those who have seen them will never forget them. That's definitely a day that I will never forget. The anxiety of not being stuck in that, what was it, kaolinite plant overnight while the stream dropped, has never left me. But anyway, my question was really, you mentioned two motivations for doing this work right at the beginning, which was water quality and flood risk. So just in terms of your public communication of the results, or communication of the results to policymakers that might need to know about these things, can you just say a little about how that has progressed?
Yes, we are now working with the name is FetchCop. This is a federation of cooperatives. They are in charge of fresh water for the communities. We have half of the population of the province that lives, take water from the Chur River. And we are moving from a monitoring network to a forecast network. We are developing, we want to collegate the measurements with a computer here in Trelew to have an alert of the income of these floods with sediments inputs to the river, so they can have at least 3 days to prepare for the arrival of the turbidity current, turbidity wave to the valley. We are moving this way, working since a couple of years now. And the problem is that maybe it is partially resolved the problem with Starlink, but you have to consider that we have no roads, no electricity, and I didn't mention, but it's a problem of technology, but batteries die during the winter because the range of temperature can be very high, more than 20 degrees, 10 degrees under zero and 10 degrees above zero during the day. So we have very challenges here. And we are moving this way, working with public associations to have a alert and a network. May I have answer your question, Stephen?
Yes, thank you. Yeah, that's good. Yeah, thank you.
We are testing this hydrological connectivity model here in this sub-basin because we would like to reproduce this research all over the basin. I mean, 100. We have to change the scale from 100 to 1,000 square kilometers. That will be the next steps.
If I could just ask a follow-up, if no one else has got a question. In terms of sort of education about flash floods in the school curricula in Argentina, is there any scope for embedding some of the work that you've been doing to sort of...
I have not any participation in the secondary or primary school, but I have made some conferences in, for instance, we have here 28 July, the day of the arrival of the Welsh settlers. So there are always meetings, and this is a good opportunity to communicate to the population this risk. And we have here been very lucky. I have to say this word in a scientific conference. We have been very lucky because there have been extreme events during these years. The year before, 2025, I think, there was one in Bahía Blanca, and it was a disaster in this city. And there was another one in Comodoro Rivadavia in 2017, another one in the Meseta. We had the opportunity to visit the Meseta with Stephen. There is here we have the same surface, I mean 1,000 square kilometers above the cities. And in the Meseta, with the same area, we could reconstruct a flood of 1,400 cubic meters per second. If this happens here, it will be a picture like the one told by Ellen Morgan in 1999, all the valley flooded by this extreme flood. So that's why I say that we have been lucky, and this research contribute to calibrate hydrological models and to assess the possible risk scenarios.
Thank you.
Yeah, any quick questions or any comments, anyone? All right. If there is none, okay. So we can thank Gabriel again for his wonderful talk, and hopefully we will see more of your publications soon. And yeah, we will have to know about all your other research which are coming up. Yeah, Dr. Fenn, you can unmute yourself and ask. Oh.
Sorry, it was the wrong button.
Oh, all right. Okay. So yeah, thanks everyone for joining today, and hopefully we will have more such webinars coming in during next months. We'll keep you updated either through BSG email or through our LinkedIn on Blue Sky posts. Thank you everyone for joining today, and hopefully we will have a lovely week ahead and weekend. Thank you. Thank you, everyone.
Thank you so much for
Thank you,
all of
everyone.
you.
Cheers.
Thank you. Thanks, Gabriel. Thanks.
Thank you.